Why don't we go ahead and get started? So welcome back everybody to EE240. So we sort of started out last time talking about high-speed links and kind of diving into some of the stuff that you're going to need for the project. Today we'll finish up with that and kind of talk some more about high-speed filters. Just kind of a couple more logistical things. So I have actually posted the next phase of the project up on the web already. Hopefully by sort of the end of today or so, you should actually know what you need to know to do that. But obviously that means that you should have started on the first phase of the project, because the second phase you'll really be taking sort of your first phase project and kind of modifying it a little bit to actually do some of the functions we're going to talk about today. So on that note, how many of you guys have actually started the project? Finished? Okay, 2 groups, good. So obviously that's due in like 2 days, so good that everybody has started on that, but definitely get going. It should not actually be too bad, it should be fairly straightforward, but you'll definitely want to get that out of the way because, as I said, the next phase is already up. It's going to be due actually 1 week from this Friday. And then immediately after that, sort of the final phase of the project, which is really where there's a lot more freedom and therefore kind of a lot more time that you want to spend to kind of explore things, will come up immediately afterwards. So definitely make sure you get going on that. As I said, we should be in pretty good shape to kind of cover all that material by probably the end of today or so. So before we kind of dive back in, any kind of questions or issues people are running into? Yeah?
For the output capacitance, can we just model it with an ideal capacitor?
Yeah, so that output cap, it's an ideal cap to ground.
Okay.
So it's not really a capacitance. That's kind of like that's modeling the input cap of the comparator. Yeah.
So what do you mean by when you use MOM capacitors? So you mean to say like you put a capacitor with the bottom plate capacitor?
Exactly. So and I'll just sketch it right here real quick. So basically, if you put in an explicit cap for yourself, because you decide you want some extra explicit cap, which, by the way, you may or may not need here, but if you do add some explicit cap, what you should do is you should add the capacitors to the bottom plate, or really the top and bottom plate capacitors to ground, and you can use the parameters for how much those should be based on that capacitor homework that we had, and the solutions are still up on the web, so if you got the wrong answer, go and take the parameters from there. Yeah.
So are we assuming that the comparator will compare the highest value? Something that you
okay.
said in the previous lecture.
Yeah, so you should assume that, for example, if this was like, let's say that the ideal transmitted bit was something like this.
Yes.
So if your amplifier responds and does, let's say, something like that, then you can indeed assume that it'll sample at exactly the right time. Now, obviously in a real thing, that's not exactly going to happen. But for this project, you can find what is the peak of that voltage and assume that you sampled it exactly at that time.
But what is we might have a signal loss there, and that is a trade-off with power.
Exactly.
How much can we get?
Okay.
Just
well, so
to
I'm
meet
gonna,
the bit error rate spec?
Yeah,
and
so
that should be
basically the only, from my standpoint, the only higher level thing you have to meet is the bit error rate spec.
Okay.
Right? So as long as you meet the bit error rate spec, again, I don't actually care how much gain you use, how much bandwidth you use, and etc. We'll talk a little bit more about kind of the trade-offs there probably right now, but from that standpoint, you just have to meet BER.
Yeah, so for the bit error rate, when you do the noise calculations, you need to include flicker noise also, right? So it depends on like what differential pair you use. So if the length is like pretty small, your power will be like...
You may or may not need to. So it's as usual. You should actually do the integration and see what makes sense. So I don't remember. Did I give you the lower limit of the integration or not?
No.
Okay. So I'll post that on the web. But I believe you should do it from about a kilohertz to, I don't know, let's say 100 gigahertz or so.
So I guess it doesn't matter, no?
Okay, well, so by the way, how did I decide that I want a kilohertz? Yeah, that's kind of like something like my longest sequence of bits that maybe I care about before maybe I recalibrate it or something. And by the way, even if I went down to like 1 second, remember, that's not going to have a huge impact on the flicker noise you pick up, right? Because there's only so many orders of magnitude between 1 kilohertz and 1 second, and there's a lot more orders of magnitude between 1 kilohertz and 100 gigahertz. Okay? So, just to be clear, everybody, that's the limits of integration you should use in Splice. Okay? So 1 kilohertz to 100 gig. So whether or not flicker noise is important, that's for you to figure out. Any other questions on the project? Okay, good. So there was just sort of a couple quick things I wanted to sort of review a little bit from last time because we went through them fairly quickly, or in fact probably even skipped them over a little bit. And so the first one really just has to do with, if you guys remember, we had talked a little bit about basically what are some options we can use in terms of terminating the receiver. And so I showed you sort of the most straightforward one, which is really, if this was my current mode transmitter that we had talked about last time, which is really just basically a diff pair taking the digital data in with a 50 ohm load to VDD, then sort of the simplest option you can think of is just to take 2 more 50 ohm resistors and basically tie them up to VDD at the receiver. So this basically works fine. The trade-off you just run into here is that the common mode tends to be fairly high, because it's really just going to be set by VDD minus whatever the transmitted swing is divided by 2. Okay? Because you can kind of think about it, the current that sets the differential swing is the same current that's going to be flowing through those termination resistors, right? So in some cases, particularly, for example, if you wanted to get pretty high gain out of this receiver over here, you might actually want a slightly lower common mode, right? So the good news is there are a couple of things you can do to do that. And so now I'm just going to draw the receiver side of the link now. So as an example, one option you might use is, let's say that this over here was, I don't know, VTX plus and VTX minus. So again, I'm only going to draw the receiver side right now. But as an example, if you wanted to get a slightly lower common mode, then rather than tying those resistors up to VDD, you could actually just tie them sort of differentially across the transmitter's outputs. Okay? And again, this is, of course, on the receiver side. Right, so the idea here is that from a differential standpoint, this looks exactly the same. Right? I've still terminated sort of the differential thing into 100 ohms impedance, okay, which, of course, on each side means like 50 ohms for the single-ended lines, right? But the trick here is now that obviously there's no path for common mode current to flow here, right? It's only going to flow through the transmitted side. So if you do things this way, then you can get a slightly lower common mode, and actually it's sort of a fairly simple exercise. You can figure out exactly what the difference in common mode between this is and that particular configuration. Okay? So fairly straightforward option there. There's actually one more thing which is fairly common that people will do, and so I'll actually ask you guys. So what if you wanted to completely independently of the transmitter set the common mode for the receiver? Guys, is there any way you can think of to try and do that? Any sort of modifications we can come up with?
Use an external amplifier.
External amplifier. Okay, I think I can do what you're saying, but so let me maybe give one hint, and then maybe we'll get people going in the right direction. So let me do this in a different color, because it won't exactly work probably the way I want. So what if I actually just took some common mode voltage and tied it right there? So let's say, I don't know, as an example, let's say I tied that to ground. What would that do? Would that set the common mode at the input of the receiver exactly to ground? So I see one person at least shaking their head. Why not?
Well, there's a voltage divider. There's 2 resistors.
Yeah, exactly, right? On the transmit side, I've got these 2 pull-up resistors, right? So these 2 pull-up resistors would just have a voltage divider with those 2 pull-down resistors. And in fact, if you remember, since that transmitter inside of there, you know, that little OTA box that I drew is really just a diff pair, right? If I did what's drawn with the blue right here, then I'd have a diff pair driving a resistive divider, with that resistive divider setting you at roughly VDD over 2. So the diff pair probably is not going to be too happy, right? The devices might come out of saturation. Okay, so this was a nice idea, because it almost looked like I could set the common mode to the receiver. So I claim actually this is not so bad. We just have to make one additional modification, which is a little bit of cheating, but
AC couple.
yeah, there we go. You just have to AC couple, right? So let's actually go and draw that other option. So if instead of doing directly what was drawn there, I just add 2 AC coupling caps. All right, so I still have my VTX plus, my VTX minus. Now I still terminate these 2 in 50 ohms. And now to actually set the common mode into the receiver, I just tap off that center point right there. Right? Of course, these are tied together. Okay? Because now, since I have the AC couple, this column mode voltage is totally independent, at least at DC, from what's happening at the transmitter. Now, obviously, if I do this, I have to be a little bit careful. So what do I have to be careful about? Yeah.
Cap must be large.
Okay, the cap has to be large. What is the size of this cap going to set in terms of things at a higher level that I care about?
The impedance times the frequency at which.
Okay, the frequency at which what?
Or high pass corner.
Yeah, it's the high pass corner, right? So if I have a network that looks like this, if I look at the transfer function from, let's say, VTX plus to VRX plus, of course, versus frequency, magnitude, then you're going to get something that looks like that, right? So the size of that cap, of course, sets what is that sort of, high pass filter cutoff. So by the way, why do I care about that? What's bad about that high pass filter cutoff? What happened if it was at like, I don't know, a gigahertz? What would be bad? Okay, let's make it even worse. What if it was at like 10 gigahertz? And I'm trying to build a 3 gigabit per second link.
That's their data.
Yeah, I lost the data, right? I'm not going to get any of my data through. Okay, so now even if I'm building a 3 gigabit per second link, why do I claim that even if this was down at, let's say, a megahertz or 10 megahertz, why do you still have to, you still have to be careful about one thing?
You're transmitting a square pulse
Okay, you're transmitting a square pulse. What does that mean?
because it's infinite bandwidth. So
There we go. So in particular, what happens if I was trying to always transmit zeros? So I just tried to transmit 0 forever.
oh yeah, never make it.
It's not going to make it through, right? Eventually, this thing is just going to leak away, meaning the voltages here are just going to leak away and go to 0, right? So if you do something like this, you have to be careful that your data is what's called DC balanced, meaning that it doesn't have any content at DC. Because if it does, that stuff's not going to make it through the AC coupling cap. Okay. Now, by the way, these caps tend to be pretty big, because you can imagine if these are 50 ohm resistors, and if you want to push this down to like a megahertz, you need a pretty reasonably large sized cap. Okay. So oftentimes you'll actually put these sort of on the board somewhere. But just remember, if you do something like this, your data has to be DC balanced. Or, well, okay, there's some other tricks you can play if you're interested. Come bug me. But basically, bottom line, your data better be DC balanced. In fact, it better be so-called DC balanced over some number of bits that corresponds to where this cutoff frequency is. So in other words, if this cutoff frequency was at like, I don't know, let's say 10 megahertz, then you better make sure you can't ever have a long sequence of all zeros or all ones that in time is sort of long enough to span 10 megahertz. Okay, because you'll start losing that data. Does this make sense to everybody? Or? Okay.
Guarantee this.
Exactly. So there's a lot of times people will add, basically codes that will ensure that you actually have DC balance. So for example, if you've ever heard of 8B 10B, 8-bit 10-bit, basically you add an extra 2 bits onto what you're transmitting. That has the property that it forces things to be DC balanced over 10 bits. So there's other codes, for example, 6466, which similar idea. They added an extra 2 bits to try and make things be DC balanced over 66 bits. The trade-off being that obviously if you have 8B 10B, you have a 20% overhead and just you're sending these code bits that don't actually do anything useful. If you have 6466, the overhead is smaller, but the run length, meaning how many ones and zeros you can get, is larger. Or how many constant zeros or constant ones is larger. So then you'd have to push this even farther down. Great. Any other questions on this? Or? Okay. So the other thing that I wanted to just kind of quickly review or sort of maybe remind you guys is we had talked about basically if we took our sort of very simple zero order kind of receiver, where we have some sort of preamp or front-end amplifier, and then driving the comparator. Sort of the last thing that we talked a little bit about was just how much bandwidth do we actually need out of that preamp. And so again, I had basically said, well, I don't care, that's up to you. But let's see if we can kind of figure out what the trade-offs are here. So, as we'd said last time, what we kind of need to look at is essentially how is that preamp going to settle when we give it certain input bits, okay? So at least for this phase of the project, we're going to completely ignore the channel. So we're just going to assume that I have basically a perfect transmitter with a perfect channel, so that the things going into my receiver really do look like these sort of nice, perfect square bits, okay? So by the way, today, in like 5 minutes or whatever, we'll fix that assumption, but for this phase of the project, we'll do that. Okay, so if I take this nice square bit and I pass it through my preamp, let's assume my preamp is just like a first order low pass. So it just has a certain bandwidth, meaning it has a certain pole, right? So what's going to be the sort of shape of the received bit if I draw that in blue? What would that look like? What do you guys think?
Exponential approach.
Yeah, it's just, initially it's going to have an exponential approach over there. Then once the bit goes back to 0, it'll exponentially decay away, right? Okay, so now as an example, let's say that this receiver, it has a certain tau, okay, or at least that front-end amplifier, meaning it has a certain bandwidth omega. So remember, this right here is the bit time, right? So let's say that I set my whole thing up so that the bit time is 2.3 tau. What would be the sort of residual error I'd get right there? How far from the transmitted voltage would the output of my receiver get? Assuming a gain of 1, of course, or in a normalized way.
10%.
Yeah, it's 10%. Remember, it's that 2.3 tau per decade. That means I'd get to within 10% of the final value. Okay? So, let's see if we can kind of use this to figure out a little bit as to what would be sort of a reasonable choice for the bandwidth. Okay? So if you guys remember, I had said last time that a typical choice for the bandwidth is to set it to be, actually it's the frequency, is to set it to be at about 2 over 3 times 1 over t bit, right? That was kind of the rough rule of thumb that I gave you. So now here's the first interesting question. Let's say t bit is like 200 picoseconds, meaning I have 5 gigabits per second of data. So if I followed this rule, what I would basically be saying is that I should set my bandwidth at something like 3.33 gigahertz. So now, usually when people first hear this, they're kind of a little bit confused. Because I just said that I have 5 gigabits of data, but only 3.3 gigahertz of bandwidth. So, why is it that I claim that actually that's perfectly okay? Yeah, right? It's that, that guy called Nyquist, right? So if I have 5 gigabits per second, the fastest thing I can do from a frequency content standpoint is just transmit 101010, right? Well, if each one of these things is 200 picoseconds wide, my frequency is, of course, 1 over 400 picoseconds. In other words, 2.5 gigahertz, right? So actually, just based on that, you'd already say, okay, if the Nyquist bandwidth is like 2.5 gigahertz, then it makes sense that I don't need more, a whole lot more than that, right? Now, it does turn out you want slightly more than that. And the reason is, by the way, again, this is just a rough rule of thumb. For your phase of the project, you should feel free to just figure out what it really should be. But the reason you don't need a whole lot more than that is, again, just simply the fastest thing you could possibly sending in from a frequency standpoint is 2.5 gig. So if you don't want to get too much loss off of that, meaning you really want to fully resolve that 2.5 gig thing, okay, you make your bandwidth about 2/3 of that. Okay? Now, again, by the way, you'll see that if you really work it out for this first phase of the project, you can actually get away with a lot less than this. By the way, just to remind everybody, why would you want to be able to get away with a lot less than that? Yeah, it's going to cost you less power, right? So in fact, that's one of the things you should be doing in this project is figuring out, okay, what's the gain I should be using and what's the bandwidth I should be using to really minimize the amount of power I have to spend to make this whole thing work. Okay? Just be notified that the optimization you come up with, assuming a perfect bit, will not exactly work once the channel itself has some badness in it. Okay? But for now, it's actually kind of an interesting thing to work out. So, any other kind of questions on this? Or? Okay, so just key thing to remember is anytime somebody says like 5 gigabits per second or 10 gigabits per second, the maximum frequency is always half of that. Just, it's a standard Nyquist thing. Okay, and the rough rule of thumb, make your bandwidth about 2/3 of the data rate in, converting bits to hertz. Okay? Okay, so unless there's any other questions on this, let's actually go ahead and move forward. So now that we've kind of learned a bit about just what do links look like and what are some of the key issues, what we had kind of talked about was, once we looked at sort of what the channels looked like, we said there was something like 20 to 30 dB of loss at sort of our Nyquist frequencies, or meaning at ranges of frequencies we were interested in. We said, okay, well, how bad is that? How important is it? We had said there was really sort of 2 issues we needed to talk about. So the first was just basically how much noise was going to be in our system, and therefore what's the smallest signal we can tolerate. Okay? Well, we said there was actually one more really important thing, and that's this so-called inter-symbol interference. So all that means is, and I'll sort of dive into it more in one second, because this channel basically doesn't pass all frequencies equally, when you transmit a nice clean square bit, what you get back out at the receiver is messed up. Okay? That mess up is like somehow it's a filtered version of what you transmitted. So it's going to turn out that if it's too messed up, you won't actually be able to decode the bits that you had intended to send. So let's see sort of an example of that. So here again, I'm just sort of repeating what we just said. So let's say that this blue waveform right here, that's what I transmitted. Okay, so that's like my ideal digital pulse. So now if we pass it through, as an example, one of those channels that I had shown previously, almost all of those have some low-pass characteristic. Well, low-pass characteristic basically means that you take anything that was sort of sharp in time, and you're going to spread it out, right? So that's kind of exactly what you can see happening on this green waveform here, which is the received pulse. So now, just to be clear, these black dots that I sort of annotated onto that waveform, those are sort of like, what are the voltage samples at the time when my comparator would make a decision? Okay, now obviously, I could have moved this around to the left and right in a sort of finer way, but I happened to choose it such that the comparator, when it really is supposed to make the decision, will get the largest amplitude. Okay? So just to kind of give you some terminology, this point right here, where you have the largest amplitude, is usually referred to as the cursor. Okay? Don't ask me why, it's the cursor, and we'll talk about how we use that in 1 second. Okay? So, you can see this thing basically got sort of spread out due to the low-pass filter. You can actually see there's also some other weird, funny-looking stuff. There's like these little ripply things going on over here. Anybody have an idea what those little ripply things are coming from, physically? Yeah, those are reflections, right? And in fact, by the way, if you look in the frequency domain, when you see these things that look like this, with like a deep notch, that's a reflection. And that's why, remember, anything that looks like, has a narrow bandwidth centered at some upper frequency is going to look like that, right? Because if I either had a spike up or a spike down, it's sort of telling you, okay, either that frequency just doesn't make it through, or I'm amplifying things at that frequency. So you tend to see these ripply things when you have these either notches or peaks in the transfer function. Okay? But so indeed, this little junk that's happening over here, that's just reflections off of various discontinuities in the system. Okay? So now, let's see why we should sort of care about this. And again, this should be somewhat obvious. So what I'm doing here is now, rather than just transmitting a single 1, I'm actually going to transmit a 1, a 0, and then a 1. Okay? And so what I want to do is, basically this green curve that's the response from the first one that I sent. Okay? This blue curve, that's the response from the second one that I sent. So now if I want to understand, like, what am I going to receive on the other side after having transmitted this 1, 0, 1, basically all I have to do is add together the green curve and the blue curve, which actually results in this red curve right here. Okay? So now there's a couple of interesting things to notice about this red curve. So first of all, if I was to sort of place a threshold somewhere and ask you what bits I received off of that red curve, what bits do you think you'd say you received? Let's just say I arbitrarily decided my threshold was here. What bits do you think you received?
4 1s.
Yeah, well, 3 ones probably, or maybe even 4. Yeah, I guess the way I drew it, I would have received 3 ones, right? Because these black dots. Oh, actually, no, you're right. I would have gotten 4 ones. Ah, good catch. Right? Because the black dot right there is actually above this line. So you're right. I would have actually said I got 4 ones. Well, that's bad news because I transmitted just 2 ones, right? Okay, so maybe I was a little bit more clever. Maybe I actually put my threshold here. But then looks like I'm going to get 3 ones, right? And in fact, by the way, turns out if I was to really do this right, because if I actually transmitted a long chain of 1s, eventually the signal would go all the way up to 1. Turns out what I really actually am supposed to do is set my threshold right there. So in fact, this channel is bad enough that I wouldn't even have received any of the 1s correctly. Okay? But kind of the key point here is the reason things are getting messed up is that essentially, as an example with this blue pulse and the green pulse, basically the green pulse is still sticking around, right? It's leaving some residual energy there. And in fact, even the blue pulse, even though it hasn't arrived at the receiver yet, is starting to actually move things in the wrong way. Okay? It's actually like pushing this signal up, even though it hasn't actually arrived yet. Okay? So first, let me just give you some sort of definitions of things. So the fact that you have these samples left over after you transmitted a bit, that's what's known as intersymbol interference. Okay? So people like to sort of categorize these into 2 different types of interference. So, and it's really just related to where in time it sits relative to when you receive the peak. So all of these dots that happen afterwards, that's what's called post-cursor interference. In other words, it arrives after the cursor. All of the dots beforehand, that's called precursor interference. In other words, it actually arrives before your maximum signal amplitude. So now here's the sort of interesting question that people typically either get confused by or are wondering about. How in the world is it possible that I have precursor ISI? How is it that something can actually arrive before my main signal does? Like, am I breaking causality here? Okay, Dan's shaking his head, but let's maybe get somebody else.
Because it's just that it's a square pulse, so the higher frequency components are getting there before the lower frequency.
Ah, okay. So that's usually that's like the physicist answer. That's like there's dispersion. It's actually exactly correct, by the way. So it's saying something like there's dispersion. The high frequency components arrive first, and then the low frequency components arrive later. That's actually correct. But I want just sort of a very simple physical, intuitive kind of thing. Why is it perfectly okay that there's some amount of the signal starting to arrive here before the main thing actually gets there?
It takes time to charge capacitors.
Okay, that's kind of true, but I guess what I'm getting at, maybe just to be clear, what I'm getting at, the reason I'm not breaking causality is that I launched the energy at this time, right? So the fact that some piece of it arrives over here, as long as that's after this, that's totally okay, right? So you're right, it takes some time for things to actually slow up, and actually if that time is large enough, it can take longer than your bit period to actually reach that sort of maximum signal amplitude. Right? So that's absolutely correct. Kind of the main point here was just, don't worry, precursor is totally valid. It can indeed happen. It just has to do with the fact that everything takes time to get there, and some pieces may get there earlier. Okay? Now, by the way, maybe just to point out one thing that should also be obvious. What's kind of the what would set sort of the bound on how much time it would take to get from here to there?
See.
Yeah, speed of light, right? So if I told you that I was traveling over a meter, let's say, and somebody told you, oh, it got there 10 picoseconds later, and you say, oh, really? That's kind of interesting, right? So again, the kind of the trick with all these things is you can actually look at, if you know how much delay it took you to get there, that really means that essentially tells you how much length you traveled to get from the transmitter to the receiver. So, but again, for sort of today, the main thing that we're going to focus on is how does this channel basically mess us up, meaning create these ISI. And therefore, what are we going to do to actually try and fix those errors that are going to be caused by the badness of the channel? Okay? Does this sort of make sense to everybody? Or? Okay, so turns out the way to sort of solve this ISI, which again is just intersymbol interference, is a fairly well-known technique. So there's, well, I guess I should just mention one other thing. So this thing here is really just a linear filtered version of the transmitted signal. Okay? That means that if I doubled the size of the transmitted signal, I'm just going to double the size of all of these dots here, right? That means that if the ISI was bad enough, that basically all of this residual signal energy was larger than what I'm actually trying to receive, then changing the transmit swing isn't going to fix it, because all of those errors are proportional. Okay? So that basically means that, in general, I can't just use larger swings to actually fix these types of problems with the channel. I actually have to do something else. And the something else is what's called equalization. Okay? So the idea is actually very straightforward, and it's something that maybe if you've ever looked at any audio equipment or anything like that, you're probably actually already familiar with. So let's just sort of draw a conceptual picture here. So let's say I have my transmitter here. That transmitter basically goes through some channel, which I'm just going to model as being some h of s, okay, some linear filter, and then goes into my receiver. Okay? Well, so if I want to fix the badness caused by the channel, at least conceptually, what I can basically do is inside of that receiver, just stick the inverse of that channel, and then receive the data, right? So of course the idea here is that if I stick that inverse of the channel inside of the receiver, then what I should be getting is h of s goes through h inverse of s, so that what shows up right here should be like my perfect digital bits, right? So by the way, this is called an equalizer because this is kind of like saying that if this introduces some frequency selectivity, meaning some different gains at different frequencies, what this thing is doing the opposite of those gains, so that the response over all frequencies becomes the same. Okay? So very simple concept, but we'll see it's actually sort of fairly interesting to actually build. Okay? So let's think about sort of what this would imply in our context. So as we had talked about a couple times, most of the sort of channels we're interested in are basically low pass in nature. In other words, they're going to look something like sort of like this, right? So if that's the magnitude of h of s, and that's omega, they're going to look something sort of like that. Okay? Where, as an example, let's just say that, I don't know, I'm going to make it up, let's say that that's at 1 gigahertz. Okay, so if I wanted to build an equalizer for this particular channel here, what would the magnitude response of that equalizer look like?
A 0 at 1 gigahertz.
Okay, it'll be a 0 at 1 gigahertz. So there'll be something that'll be doing this. How about like, the DC gain? By the way, let's just pretend that's 1 right there.
0.
Yeah, same. It's just 1, right? So I should have something that basically, and let me draw that a little bit more cleanly, that basically does that, right? So now, by the way, I never sort of explicitly said what type of channel this was, meaning if this is like a first order roll-off or second order, but let's, as an example, assume it's a first order channel. So let's say that's a single pole at a gigahertz, then indeed, if I build the inverse, it should just be a high-pass filter with a 0 at 1 gigahertz. Okay? So now, here's sort of one question which we'll see sort of relates into a couple of interesting things. So the question is, do we need exactly H inverse of S? In other words, what would happen if in my equalizer I didn't use exactly this transfer function, but something else? Question is, would that still be okay? So let's maybe take a poll. I've seen a couple of nods and shakes. So who thinks I always need to use exactly H inverse of S? Not exactly H inverse of S? Okay, good. So now, what's allowed? What can you do that is okay?
Well, can you ever exactly have H inverse of S?
Ah, that's an excellent question. We're going to come back to that one in 1 second. Yeah, go ahead, Shiva.
I think it'll depend on your comparative threshold, like how much it can resolve.
Ah, okay. Actually, so you're sort of right. That's sort of more sophisticated. I even want something maybe simpler than that. So what's like the dumbest thing that you could do that would still sort of technically be okay as long as, let's say, your comparator was sensitive enough? What's one really simple thing you could do that would still sort of give you nice square bits? Ah, yeah, you made the right motion. Just speak up.
Lower. H inverse as is lower than what you actually need.
Okay, well, when you say lower, what do you mean?
DC gain is less than 1.
There we go, right? I can multiply this thing by any arbitrary scale factor. And as long as I still get enough noise, as long as my SNR are still good enough, that's still perfectly fine, right? I'll still get something that's flat over frequency. So that's definitely correct. Now, actually, let's go back to your question. You said, can we ever actually get the perfect H inverse of S? So I claim probably not. So what's the problem? Why can't we get exactly that transfer function?
Because you're running up against the bandwidth of the transistors.
Ah, okay. So let's maybe even, you're absolutely right, by the way, but let's even make it a little bit more explicit. What do I have to do to get exactly H inverse of S?
You need infinite energy.
Yeah, I need infinite gain at infinite frequency, right? Sorry, not going to happen. I mean, even if I had infinite power, still I don't think that's going to happen, right? So what is that kind of saying? What's also sort of okay then? Or potentially okay?
I mean, roll off at high frequency.
Yeah, basically, what we're going to say is, well, okay, I know I can't really get like gain at, I don't know, 100 gigahertz or something like that. But as long as I get enough gain up to sort of the point I care about, then probably that's actually okay. And indeed, that's actually correct. So maybe just as sort of a reminder, what do we think, what is the point that we actually care about? How high of a frequency do you think you need to go to?
Close to the bit period.
Okay, close to the bit period. What was like the rough rule of thumb that I gave? Yeah, 2/3 of the bit period, right? So if this was our channel, which again, let's say there was a pole at 1 gigahertz. Let's say this was now going to be, so I'll just call this H of S. So let's call this H inverse of S, which of course we said that, oops, I'll just draw it scaled down over here. That indeed needs a 0 at 1 gigahertz. But we know that's going to be sort of pretty tough to actually build. So what we're basically saying now is, okay, instead, if I actually look at what's the real thing that I need, and I can actually build, let's call that like G of S, which is just my real equalizer. And what that's basically going to look like is something like this, okay? And again, my drawing's not great, so I'll just do it a little bit. There we go. Something like that, okay? So that point right there, where you get the 0, that's going to be 1 gigahertz, okay? So as an example, let's say that I wanted 6 gigabits per second. Where would this point right here be? What frequency would that be at?
4.
Yeah, 4 gigahertz, right? Okay, so now there's actually sort of something that we need to be sort of careful to notice here. That point right there actually has 2 poles, not just one. Okay? As we're going to see in 1 second, one of those poles basically just has to do with the bandwidth limit of your amplifier. Okay? Because again, your amplifier just beyond a certain frequency, it can't get anything through it, right? The other pole actually has to do with the fact that no matter what network you build that creates this 0, you can never get infinite gain at high frequencies. So anytime you create a 0 in a real circuit, it always has to have a pole associated with it too. Okay? Now, I've just assumed that both of those poles are sitting right there at the same spot. Turns out that's always how you're going to want to put them. And we'll see that, if you kind of think about the transfer functions, you can actually figure that out. Okay, but keep that in mind, because when you actually do your designs, this is a good sort of design point to target. And again, if this isn't entirely clear now, we'll talk in 1 second about how you actually build all this stuff. You'll see exactly where the poles and zeros are coming from. Okay? In the meantime, does this kind of make sense to people, or? Okay. So, now let's really see what this sort of means from the standpoint of trying to build this thing. Oops. So again, let's take a look at my channel. So let's say I have something that looks like that. So again, that's at 1 gigahertz. Now I'm going to look at sort of the actual equalizer that I build. Okay, so that's going to look, let's say, something like this. So we just said that's at 1 gigahertz. And this is at 4 gigahertz, right? So of course, there's also going to be like 4 gigahertz is sitting right over here. Okay, so I want to start thinking about how I actually build this thing. So if I'm starting to think about that, I'm probably going to be interested in things like, okay, well, certainly I need to know where these frequencies are. But I'd also like to know sort of like, how big is that sort of peaking that I have to do? In other words, if I look at the gain at DC versus the gain at the highest frequency, stands to reason that I might be interested in sort of how big that ratio is supposed to be, right? Turns out that's actually pretty straightforward to figure out. So you guys tell me, what's actually going to set that? Where's that going to come from?
Well, I think your second harmonic needs to be less than 1, because you're in a square wave, the second harmonic interferes as a fundamental.
Okay, I think yes, but I think you're being a little bit more sophisticated than needed here. Because remember, at the end, if I have a single bit, because remember, I'm not just transmitting square waves, I'm actually transmitting bits. So my goal is, if I transmit a bit, I want it to come out also looking like a square bit. Now, I can't exactly do that because, again, I need infinite gain at high frequencies. So at least I want something that sort of looks like almost perfectly like a bit to come out. Okay? So if I gave you this channel right here, which is a low-pass channel, and I told you it has a pole at 1 gigahertz, and you need a bandwidth of about 4 gigahertz, what would set this ratio of gains right here?
The ratio of gains over here. Inverse of the ratio of the gains.
Yeah, exactly. Right? So whatever the ratio of gains over here was, and let me be explicit about that. So let's say that's A at high frequency, and that's the A at DC. Whatever this ratio is, that's what's going to set this ratio of gains you need to use here. Right? Because remember, the whole point of the equalizer is to try and line all of the frequency components up, at least up to the frequency you care about. Okay? So let's actually be specific. Let's say that I told you this was a first order low-pass filter. What would A peak over ADC for the equalizer be set by?
12 dB. 12 dB.
So, okay, well, wow, you converted to dB. So it would have been a factor of 4, right? Because let's just call actually this my F bit, or actually let's call that my F bandwidth. Let's call this my F of the channel. right, then that ratio there would have been F bandwidth over F channel. Okay, now for those of you guys who really keep track of linear systems and 3dBs from 3dB bandwidths and everything, this actually turns out to get multiplied by 1/2 if you actually exactly measured this. But the bottom line point is that indeed these ratios of gains right here track with the ratio of the channel bandwidth, the bandwidth of your signal to the bandwidth of the channel, right? At least for this first order system. In other words, the faster you want to go, the larger that ratio you would need to create. Okay? So now, just to be sort of really clear, what would have happened if this channel right here was actually a second order low pass filter with both poles at F channel? How would this ratio have scaled then?
Where?
Yeah, it's squared, right? It would have then been that you need F bandwidth over F channel squared. So in other words, if I start adding more and more poles over here, it gets more and more painful to go up to higher and higher frequencies. Right? Because you have to create these really, really big peaking ratios. Okay? Does this kind of make sense to everybody? Or? Okay. So now that we kind of understand sort of what the requirements are from a kind of, let's say, almost mathematical standpoint, let's look at just sort of a couple of different options for how we could actually build these things. So as it turns out, and as you might not be too surprised to know, you can actually build the equalizer actually either at the transmitter or at the receiver. And so let's actually sort of just draw our little cartoon picture here. So let's say we have our transmitter, we have our channel, and then we have our receiver. Okay? So if you build it at the transmitter, sometimes people call that pre-emphasis. That just has to do with if I put the H inverse before I actually go through H, I'm sort of like pre-distorting or pre-emphasizing everything, right? If I put it at the receiver, I go through H first, and then through H inverse. But so, in terms of how you'd actually build something like this, in the transmitter, the way at least most people think about it is, my inputs here are like digital bits, right? So I can basically take those digital bits, pass them through some digital filter, which is usually an FIR filter, meaning finite impulse response filter, and then effectively feed it into a D to A converter. Okay? In other words, I just take the digital bits coming out of the FIR and create an analog waveform out of those. Now, it turns out there's actually some slightly more clever ways you could do that, but that's sort of the typical approach. Okay? If I do it at the receiver, and we'll look at this in more detail in a second, at the receiver, since you're receiving the analog waveform, what you'll typically do is build some analog amplifier that has this frequency shaping characteristic, and then feed it to the comparator. Okay? So either which one of those approaches will work. But now, which one do you guys think we're actually going to spend more time looking at? Do you think we're going to spend more time looking at the transmitter or at the receiver? Receiver, okay, well, yes, this is an analog class, so obviously that's a good reason. But besides that, why is it that I actually claim that most of the time you probably do want to implement this at the receiver and not at the transmitter? Yeah, it's lower power. Why is it lower power? Okay, that's a good analogy, although I'm not, well, let me maybe rephrase it a little bit. So I think I'm going to say the same thing as you did, but just slightly different way. So what did we say kind of has to be sitting out at that output right there? What's the impedance that you have to be driving? Yeah, it's going to be something like 50 ohms, right? Anytime I drive 50 ohms, that basically says, if I want, let's say, a volt of swing, I need 20 milliamps of current, right? In other words, because this impedance is low, to get a certain voltage swing, I need to spend a lot of power for it, okay? At the receiver, okay, yeah, I still need my 50 ohm term at the input, But if I've got like 30 femtofarads of cap, for example, like I told you in the project, coming from the comparator, the impedance of that capacitor, even at 5 gigahertz, is pretty high, right? A lot higher than 50 ohms. That means it costs me a lot less power to get the same voltage swing, okay? So because of that, I claim that even actually once you're doing this equalizer thing here, you tend to want to do it in the receive side, simply because that results in lower power. Now, it turns out there's some long, heated debates we could have about this, with like, I have these debates with my colleagues from other institutions about why you want to do this versus that. If you're interested, come bug me. I can tell you a whole lot more. But for now, bottom line, we're mostly going to focus on this because it turns out that that is usually the lower power way of doing things. So before I move on to actually talk about sort of how you build this, there's one just sort of last important point that I need to make. And I'll make it actually by looking at the transmitter because it's a little bit easier to see what's happening there. Okay? So let's say that I have a channel similar to what we were talking about before, so that the equalizer characteristic I want to build looks something like that, where let's say, relatively speaking, the DC gain is like 1, and the high frequency gain is like 10. In other words, there's a ratio of 10 there. Okay? So now, let's say that I tell you the peak-to-peak swing I can put out of my transmitter, let's say that that's 200 millivolts. Okay? So now, here's the interesting question, or the thing that I sort of want to use to point out. If my peak-to-peak swing is 200 millivolts, and I can't go more than that because let's say something in my DAC comes out of saturation. What does that mean these levels here will actually translate into in terms of millivolts? So if I say that I want to transmit something with a quote-unquote gain of 10, what does that mean will be coming out of the DAC? Sorry, say that again?
2 volts.
Okay, well, that would have meant 2 volts, but can I actually transmit 2 volts? I can't, right? The max I can do is 200 millivolts. So what is this level going to be in millivolts? Yeah, it has to be 200 millivolts, right? Okay. What does that mean this level down here is going to be? 20 millivolts, right? Okay, so now, how much signal is my comparator actually going to get? Or how big is the voltage swing that's going to show up right there?
Millivolts.
It's 20 millivolts, right? In fact, it's always 20 millivolts because when I transmit these 200 millivolts, that's because I know that when I go through the channel, it's going to get attenuated by 10, right? Okay, so why did I bring this up? Why is this kind of bad news?
Limits our dynamic range.
Yeah, in other words, because of the fact that I have a certain swing I can create here, and I need a certain peaking, that basically means I'm limiting my dynamic range, right? In other words, because at the end I only get 20 millivolts, even though I could have transmitted 200, it's as if I have larger noise than I used to, right? Because my actual useful signal is 10 times smaller, okay? So if you're a communications kind of guy, this is, they like to refer to this as noise enhancement. It's just a fancy way of saying that, if you have to go through a low-pass filter, and you have to equalize the thing, you're going to basically get more noise than you would have if you didn't have to do that. Okay? Now again, I'm doing this on the transmitter because it's sort of easier to see why this is happening on the transmitter. But if you don't believe me on the receiver, it's kind of a similar idea. Right? So in the receiver, basically, when I implement a function that looks like this, as we'll see in 1 second, usually the way you have to do that is if you had a certain peak gain, you're just going to have to throw away that gain at DC. Okay? That's actually usually the way you're going to have to build these things. Because unfortunately, in 90x% of the time, it's really hard to actually build things that really do truly give you more gain at high frequency. Okay? Does this kind of make sense to everybody? Or? Okay, so now let's actually sort of take a look at how are we going to build this thing. Well, the good news is, particularly from the standpoint of your project, because as I said, this is now up on the web and will be due shortly, in order to build these equalizers, which, by the way, that's exactly what phase 2 of the project is, what you're basically going to be doing is reuse the front end or preamp that you already built. Okay? But what you're actually going to do is take that preamp and effectively tie it in negative feedback through a low-pass filter. Okay? So let's see sort of conceptually how that is going to help us, or how that's going to allow us to realize this equalizer. So let's say my original design was just this preamp that has some A of S with it. Okay? Well, if I take that preamp and I want to make an equalizer out of it, then basically what I can do is I take the thing, and as I just said, I tie it through some low pass filter into feedback. Okay? Like this. And let's just call this right here H of S. Actually, let me be consistent. I'll call that G of S. Okay. So if I do this, just from a sort of feedback block diagram standpoint, or from like a mathematical standpoint, if I call this V out, what's going to be the transfer function from V in to V out for that equalizer? Just mathematically.
A over 1 plus AG.
Yeah, exactly. It's just A of S over 1 plus A of S times G of S. Okay, well, so just like our sort of classic feedback kind of stuff, let's assume A is big. And I guess I should be precise, that's V out over V in. So if A is big, what is V out over V in going to converge to? Yeah, 1 over G of S, right? In other words, G inverse of S. Okay, so intuitively all that's happening here, which again should make a lot of sense, is if I have a low-pass filter in the feedback, then at low frequencies, my signal just makes it through the low-pass filter, and I basically have a large feedback gain, right? It's almost as if I put this thing as an example in unity gain feedback, right? Once I get to higher frequencies, the filter attenuates the feedback, and so now more of my actual signal makes it through, right? So in other words, I'm exactly getting this equalizer behavior, where I've reduced the gain at DC, and at high frequencies, I'm getting more of that gain. In other words, I'm really implementing the inverse of whatever's in that feedback network there. So now, again, just to sort of make sure this is all clear, if you could put anything you wanted to into this feedback network here, what would you put? Ideally speaking, again, in our context of the high-speed link here. So what would you want to put into this feedback loop right here?
The channel?
Yeah, I want to put the channel. Okay, so now why is that slightly problematic?
Area?
Well, yeah, I mean, yeah, it is actually area, but it's not even just your chip area. It's like the entire board, right? Because you'd have to take the entire trace and everything and somehow take it out and come back. I don't exactly know how you do that, right? But you're exactly right. You want to put the channel, right? So the bad news is you can't really do that. The good news is most channels look like low-pass filters. Okay, so how do you build low-pass filters? RC, right? So actually, you can basically fake the channel almost by building an RC. Now, reflections are a little bit more complicated because they have these like sharp notches and junk like that. So those are a little bit more fun to deal with. We're not going to worry too much about that here in this class, but what we're going to see in a second is most of the equalizers that you actually will be interested in building will essentially use some sort of RC filter in some form of feedback to create the response that we want. Okay? Does this make sense to everybody? Or? Okay, so let's actually take a look at how could we really build something like this in the actual circuit. Okay? So let's just start out with kind of the simplest thing that matches that block diagram the closest. So let's just say I start out with some original preamp. Okay, some fairly simple, just, common source OTA. Okay? So now, if you guys remember from sort of the block diagram, conceptually what I'm going to want to do, if those were my outputs, what I'm going to want to do is take those outputs and somehow low-pass filter them, right? So like we just said, hey, RC circuits are great low-pass filters, right? So why don't I just take those two outputs and filter them through some RC circuit? Okay, so now what I want to do is somehow I want to take those low-pass filtered versions of the output and feed them back, right? All right, so anybody have an idea what's like a really simple thing I could do to try and feed those things back? By the way, this doesn't have to be like optimal in any way, shape, or form. Just what can you do?
Tie it to the inputs.
Okay, well, I guess I could try and tie it to the inputs. I have the minor problem there of those are like 50 ohm terminated. And if I have an RC filter, I probably don't want to have 50 ohms or anything, right? So
Use an amplifier.
there we go. I could just use another amplifier, right? So why don't I just take another amplifier and basically use that amplifier. And actually, let me draw this a slightly different way just so that I don't get the polarities reversed. So I'm going to do it, yes, there. As an example, I could have that one grabbed from there. And this one would be grabbed from here. And of course, some current source over here. Again, sorry for the redrawing. I just wanted to make sure I didn't actually create a positive feedback loop instead of a negative feedback loop. Okay, but I think I got it right. Okay? So if you don't believe me, just walk from here to there. At DC, it looks like a diode-connected transistor, right? Which is basically saying at DC, it's tied into some sort of negative feedback. Okay? So if I was to build this thing, as we had basically said before, what I'm essentially doing is, if this was my original amplifier transfer function versus frequency, what am I essentially doing here? How am I basically modifying that amplifier's transfer function? What will this connection right here do? At least, let's say at DC. So let's say, again, originally I just had this amplifier right here, and none of this stuff existed. So that's what this would look like. So now, when I add this piece in right here, let's maybe add some labels in here. Let's say that this thing has a certain GM1, and this thing has, let's say, a certain GM2. At DC, what would the gain of this whole thing be? Not a trick question, by the way. So what does this thing look like at DC?
Unity gain feedback.
Yeah, this piece is sort of in unity gain feedback, right? So what's like, if I was to look at that node right there, what's the impedance at that node, at DC?
1 over GM2.
Yeah, it's just 1 over GM2, right? Okay, so what would be the DC gain? From V in to V out.
GM1 over GM2.
Yeah, it's just GM1 over GM2, right? Okay, so in other words, if I used to have, as an example, if this A used to be, let's say, GM RL, now what I'm actually going to get is GM1 over GM2, right? Okay, so now let's just call this R and C, and of course that's also R and that's also C. At what frequency would you start to get a gain that's different than that out of this closed loop structure here?
1 over RC.
1 over RC, right? Because once you hit that frequency, instead of this being diode connected through a gain of 1, it's going to be a gain of less than 1, right? And as you go up to higher frequency, the gain drops linearly with that frequency, right? In other words, what's going to happen is you're going to start to get something that does, well, let me draw that a little bit better. Let's start doing this, right? So that's just 1 over RC here. Okay, so now, what would happen? There's sort of like 2 things that we need to keep in mind here. So, first, we know that the amplifier by itself, it has a finite bandwidth, right? So clearly, I'm eventually going to have to get a pole just from the amplifier by itself. But actually, I'm going to pick up another pole. Okay, that other pole is just coming from the following thing. We said that at DC, that feedback connection there creates a 1 over GM, right? But so now let's not, usually we ignore ROs. Let's not ignore RO this time. So, at high frequency, what's the maximum impedance you'd see looking down into there? What would that be? And by the way, when I say high frequency, I mean so high that, the low-pass filter has basically, the gain has gone to 0.
RO?
Yeah, it'd be RO, right? In other words, even if I didn't have any cap at all sitting on these output nodes right here, this structure right here would still have a pole in it. Simply because if I looked at that Z in, if at low frequency it was 1 over GM2, eventually it has to be RO, right? Which means it's going to have to do something like this. Okay, in other words, if it has a 0 at one spot, it's eventually going to have a pole. Of course, the ratio between the pole and the 0, that's exactly what sets that peaking gain right there. Okay? This sort of makes sense to everybody here? Okay. So, I guess if you don't trust me already, trust me, if you build this, it'll act like an equalizer. In other words, it'll indeed give you some transfer function, maybe that I'll draw in blue here. It'll indeed give you something that looks like it has a 0, and then 2 poles, and rolls back off. Okay? But here's the question for you guys. Is this a good equalizer design? Well, so hopefully by now you know from my tone that it's clearly not a good equalizer design, or maybe not the best equalizer design, but of course, why is this not necessarily the best equalizer design?
Gain.
Gain. Okay, so what about the gain?
It's close to 1, but you need some.
Okay, well, the gain is going to be set by that ratio of GMs.
Right.
That's certainly true. Unfortunately, just about every single equalizer I build, and if you remember I said this before, that every time we build an equalizer, it's going to have to be that rather than getting extra gain at high frequency, we're actually going to throw away gain at DC. Unfortunately, most equalizers are going to do that.
You're screwing up by putting a resistance in there, right? The noise.
Okay. So you said a couple of things there. So this resistor here, yeah, it's probably going to add a little bit of noise, but I claim that's probably actually not that big of a deal. But there's definitely something else that is going to be adding noise.
You need to have a lot of gain in the amplifier, so that'll burn power.
Which amplifier?
The main amplifier.
Okay, did I really change anything about the main amplifier?
I mean, you need a lot of gain to maintain the feedback, right?
Well, okay, I mean, notice the feedback is actually happening over here, right?
No, I mean, the approximation is valid only if the...
Yeah, but that's talking about this amplifier. That's not this amplifier, right? Notice the feedback is happening through there, not through here, right? But actually, I claim you're maybe going in the right direction.
The output impedance has changed for the main amplifier.
That's true, although it turns out I was actually using that change in output impedance in order to build the equalizer, right? Because if this was my output impedance, that's exactly how I got this transfer function.
feedback amp needs more bandwidth than the main amplifier?
Yeah, I think their bandwidths are actually basically the same, right? Because they're driving the same capacitive load. Right? There's the same cap sitting out on the drains of both of those guys. So I think their sort of GM over C is actually just set by the ratio of GMs. There's something even actually simpler than this.
2 stages of power.
So,
Is it a noise?
does that amplifier right there give me any extra bandwidth?
No.
No, right? What is the only purpose that amplifier is serving?
Impedance.
Yeah, all it's really doing is it's lowering the impedance at DC, right? So in other words, I'm spending power to basically throw away gain. Not only that, what happens every time I have a device with a GM tied to my output? What do I also add?
Noise.
Noise, right? So in other words, the reason I claim this way of building the equalizer is quote-unquote bad is because I've added extra power consumption here, and I've added extra noise, and the only thing it's doing for me is actually selectively throwing away gain at low frequency. Okay? So in other words, what I would really much rather prefer to do is somehow reuse this same amplifier without changing its power at all, but just selectively throw away gain at low frequencies. Okay? Because if I can do that, I can get the same transfer function, I can get the same functionality, but I don't have to actually spend extra power for it, and I don't have to add extra noise for no good reason. Okay? So actually, just based on that, anybody have a guess as to what else you can do to make it so that you don't change your power at all, or at least in a very minimal way, but just throw away gain at DC? Maybe somebody other than Shiva and other than Eric, just to get some diversity. What can I do to throw away gain at DC?
A capacitor in series.
Okay, but I want to throw away the gain at DC. So you're right, I would throw away infinite gain at DC if I did that. So I don't quite want infinite loss in gain, but so I want let's say I wanted to, I want to control that somehow.
Source degradation?
There we go, source degeneration, right? So let's say I take my differential amplifier. Okay, normally when we draw differential amplifiers, we draw them with the tails shorted together. But if I wanted to build source degeneration, I could actually split those two tails into two different pieces. And so now, okay, I still want some gain at DC, right? So what I do is I put some resistance across those 2 points, right? Let's call that RS, okay? So, at DC, what would be the effective GM that you'd measure out of this thing from a differential standpoint? What would that be? Just, for a standard source degenerated thing.
M over 1 plus GM plus GMRS.
Yeah, so for a standard source degeneration, let me call that GM effective. That's going to be GM over 1 plus GM RS. Okay, now we just have to be a little bit careful. So notice how I tied this source resistor up. It's tied differentially across those 2 inputs. There we go. So it's RS over 2. Because remember, Miller effect, it's not just capacitors. If you double the voltage across a resistor, you get twice as much current, half the impedance. Okay? So it actually would be GM over 1 plus GMRS divided by 2. Okay? So in other words, if my GM was large, my effective GM would roughly be 2 over RS. Right? Okay. So, now, I didn't just want to throw away gain at DC, but I wanted it to come back at high frequency. So how do I make it come back at high frequency? What do I add?
Capacitance.
Capacitor, right? Where do I tie that capacitor?
You just
frequency.
Parallel to RS.
Yeah, it's just parallel to RS, right? Let's just call that CS.
Oh, yeah. Sure.
Because all that capacitor is doing is at high frequencies, you want to get the full GM back. In other words, you want to short the two tails together, right? Well, how do you do that? You put a cap in parallel so that at high frequency, the impedance of that cap goes to 0, right? So now, at high frequency, of course, the GM, the effective GM, will just be equal to the nominal GM, right? Okay, so good news. Actually, I claim I'm basically done with that equalizer. Okay, because I just put whatever load I had before into the up at the top over there, and I actually indeed will have the equalizer. Because again, at low frequency, I've thrown away the gain, and at high frequency, I get the gain back. Okay. So now, just to be clear, what is the frequency at which you hit the 0? In other words, the gain starts to pick back up.
SC.
2 by R6.
Yeah, so that's just 1 over RS CS, right? Okay, so now remember, as I just explained a second ago, I can't get infinite gain at high frequency. Or to say it another way, if at DC this was my effective GM, at high frequency this is the maximum GM I get, right? So just based on that, what's going to be the pole introduced by that degeneration network? What's that going to be set by?
GM over CS?
Okay, you actually got the right answer. It turns out to be GM over CS. There's a factor of 2 you missed there. But let's see if we can get to that in a sort of intuitive way. So what did we say a second ago that the pole was going to be set by? And I think I have that on this slide right here. What sort of sets, if this is a certain omega z, and that's an omega p, what is that directly related to? If it was a first order thing, which this is a first order thing.
The ratio
GM
of
over.
Two failures.
Yeah, it's related to the ratio of the peak gain to the DC gain, right? So in other words, if I wanted to know the pole for this, I could just say, okay, I know at high frequency my effective GM is just GM, and at low frequency, my effective GM is just 2 over RS, right? Okay, well, so that's the ratio of gains I have. So if I take the ratio of gains and multiply it by the 0 frequency, that should give me the pole frequency, right? Because the ratio of the pole to the 0 has to be the same as the ratio of the gains. It's a first order system. That's the only thing that can happen. Well, okay, if you work that out, of course, what you get is GM over 2 CS. So just in case it wasn't clear, where'd that magic factor of 2 come from? Let's, our buddy whose effect we quote all the time. Miller effect, right? Because we tied those caps up across the 2 differential. Okay? This sort of makes sense to everybody, or? Okay, so now, since many of you will probably try and use this particular equalizer, there's just one thing you have to be really, really careful about here. Okay? So everything I just said here works really, really nicely as long as you have really big ROs. Okay? Unfortunately, if RO is not that big, then whatever you have sitting at that output over there is going to interact with what's happening down at the source over here. Okay? So all of the sort of nice equations and everything I've written here, just be warned, you have to be a little bit careful. Because if you don't have really great RO, you can get some, let's say, interesting phenomenon happening once you try and build the thing. Okay? But, you guys will get the chance to sort of see that. Okay, any sort of other, yeah? Sorry?
Why can't you put a cascode?
You can put a cascode. Please, feel free, go ahead, put the cascode. You'll see there's still some more fun you might have, but that is a very good suggestion, right? Side claim, you probably do want to put the cascode even. But again, you'll see life isn't quite so simple. Any other questions on this, or? Okay, so I think we'll break here for today, and we'll finish this up on Thursday. So see you guys then.